All right, this is question number 1 on the simple harmonic motion and waves practice problems. With this first problem, we have a block, and the block is oscillating and moving from a position of max spring extension to max spring compression in 0.25 seconds. You are asked to find the period and frequency for this motion. Please recall from previous units that the period, denoted with a capital T, is the amount of time per cycle, and that is in SI units seconds. Also recall that the period and the frequency are inversely related. Let's look at a schematic. Now, we looked at this a while ago when we studied the work energy theorem. Please note that in areas of maximum extension and compression, we have the greatest restoring force and thus the greatest acceleration. Also recall, as an object moves through equilibrium, it has its greatest velocity. However, at that point in the middle, we have zero acceleration and we have zero force. However, we do have the greatest velocity. Let's get to this problem here. So, period is the number of seconds per cycle. We are given the amount of time, and this is 1/2 of a cycle. Now, it's important to look for that information because we are told explicitly that it moves from max extension to compression. Well, that is only 1/2 of a cycle. Remember, a full cycle or round trip, this block would have to return back to an area of max spring extension. So in this diagram here, we're only showing 1/2 of a cycle. In order to be a full cycle, again, the block would have to return back to max extension. So we get 0.5 seconds when we solve this problem. And again, the frequency is simply the inverse of the period. So with numbers in for there, we get a frequency of 2 hertz. This is named after a great German physicist, Heinrich Hertz. And also recall that hertz are equal to the inverse of a second. Now, in question number 2, a student is observing an oscillating block and counts 45.5 cycles, so full round trips there. And in 1 minute or 60 seconds, you are asked to determine the frequency and period. Again, recall that period is nothing more than cycles, or the number of seconds divided by cycles, and that the period and frequency are inversely related to one another. Also recall that for an object in oscillatory motion, we would have the maximum restoring force at these areas of max extension, max compression. Therefore, because the force is maximum, the acceleration is maximum. However, when the object passes through equilibrium, it has its maximum velocity, but the force and acceleration are 0 at that point. Let's get to the problem here. Number of cycles, or number of seconds per cycle. We know that in 60 seconds or 1 minute, we have 45.5 cycles, which gives us a period of 1.3 seconds. We know that frequency is inversely related to period, so we can easily calculate the frequency to be 0.76 hertz, or the inverse of a second. Question number 3, we have a block and its mass is 2 kilograms and it's attached to a spring, and we are given the spring force constant, K. All right, you are asked to calculate the frequency and the period of the oscillations for this spring block system. So I have this schematic that's been in the last couple problems to remind you of areas of max force, max acceleration, and also maximum velocity. Also, please recall that the force of a spring is given by Hooke's law, named after the great British physicist Robert Hooke, which states that the force of the spring is equal to the spring force constant multiplied by the position. Also remember, this negative sign is there because it is a restoring force. If the spring is extended far to the right here, its restoring force will be opposite or to the left. Let's get to the problem. So this equation that is in the preceding facts on the problem set, you've watched some videos and podcasts over it, states that the period is equal to 2 pi multiplied by the square root of mass divided by that spring force constant. So if we put in our numbers here, we have the mass, we have the value for K, which means we can simply plug and chug to get the period is equal to 0.51 seconds. Now, you know we're going to be talking about this equation semi-quantitatively using some mathematical reasoning, but for now you're just getting a feel for how to use the expression, how to use the numbers, what variables you need, etc. Now, the frequency is inversely proportional to the period, so we can calculate that to be about 2.0 hertz. Question 4. A block is attached to a spring and set into oscillatory motion, and its frequency is measured. If this block were removed and replaced by a second block with 1/4 the mass of the first block, how would the frequency of oscillations compare to that of the first block? See, I told you we were going to use some semi-quantitative reasoning here. Let's look at our equation. So the frequency is the inverse of 2 pi, and that multiplied by the square root of the spring force constant divided by the mass. So if we look at this, and again, this animation is ideal for showing the fact that in areas of max extension and compression, we have the greatest force and thus the greatest acceleration. Also, we have at equilibrium, we have here the greatest velocity. Just keep that in mind for me, please. Let's look at the fact that frequency is proportional to the inverse of the square root of mass. All right, mass is in the denominator under the radical, so our expression for comparing using mathematical reasoning is force is proportional to the inverse of the square root of mass. So we are told in the problem that this second block has 1/4 of the mass. So if the first block was, say, 16, remember, we can make up numbers to help conceptualize a problem. There's no reason why not. So in this case here, if we had a mass of 16 for block 1, and we look at the mass of block 2, which is 1/4, so 16 divided by 4, we get 4. So we have these proportionalities set up for us to compare. And also, because mass is in the denominator, as mass goes down, frequency goes up. Now, it's not directly proportional because it is under the radical. It's a square root relationship, so you need to watch that. That's why I've made up simple numbers to conceptualize this problem. If the mass decreases by a factor of 4, then the frequency is going to increase by a factor of square root of 4. So it's going to go up. And square root of 4 is 2. So the frequency doubles. And I hope that makes sense. If we've gotten to do the labs yet, this should make perfect sense. So we put on a smaller mass and frequency increases. That is because of this inverse relationship where the mass is square root. It's under the radical. Please watch that. All right. Now, in question number 5, a student performs an experiment with a spring block simple harmonic oscillator. In this first trial, the amplitude is given as 3 centimeters. In a second trial, using an identical spring block system, the amplitude is 6 centimeters. So trial 1 has a smaller amplitude compared to trial 2. You are asked to compare the values for the period, frequency, and the maximum speed of the block between these two trials. Now, the whole purpose for this question is to accentuate the fact that the period and frequency are independent of the amplitude. What that means is, regardless of the amplitude being 3 centimeters in trial 1 or 6 centimeters in trial 2, the period and frequency will be the same. Let's look at why. We have first the same spring and block system, so they're identical. Next, the period and frequency are the same. I want you to understand why, and that has to do with the fact that the maximum speed in trial 2 is indeed greater than it was in trial 1. So because of a greater amplitude, 2 times the amplitude in fact, in trial 2, this block will have a greater speed. So it can go through the same distance and complete the same cycle in the same amount of time, and thus the period remains the same. And because frequency is the inverse of a period, the frequency also remains the same. Let's look at something really cool. This is called a tautochrone. And what a tautochrone is it's also referred to as an isochrone, and iso means same. Well, this curve, which is the path produced by a cycloid, and a cycloid is the path traced by a point on a wheel rolling in a straight line without slipping. Really cool stuff. But anyways, what this shows is that the time that it takes to reach the bottom of the tautochrone is the exact same for all 4 of these objects. Now, you may note that the blue ball is considerably further away. It is traveling a greater distance in the same amount of time. And the reason for that is because the blue ball has a greater acceleration and a greater speed. So it is able to go a further distance, but in the same amount of time. Now, this graph here is showing the position S as a function of time. Now, you can see there that the yellow ball has a greater initial starting position. However, it goes in that same amount of time as the blue ball, even though the blue ball goes much further. So it is independent of the path and has the same amount of time. I thought this would be a really cool way to make sure you understand that the frequency and period are independent of amplitude. Question 6 is a ranking task. We have 4 different spring block oscillators. We have different amplitudes, which we just went through a lengthy intuition in question 5 over how amplitude is independent of frequency and period. It's not going to affect those. If we then say what will affect the period is the fact that the period is directly proportional to the square root of the mass and proportional inversely to the square root of the spring force constant K. In other words, as K goes up, period goes down. As mass goes up, period goes up. But again, be careful. Notice both of those are under the radical. So please be vigilant of that. Be aware of that. Make sure you're not falling for one of these directly proportional. Yes, it is, but it's under a radical. So the square root of mass, the square root, the inverse of the square root of k. So if we look at these, let's go ahead and get some information out. So A, we have the greatest mass out of all, 10 kilograms, but a smaller k, relatively speaking. Whereas in B, we have a large mass, a greater mass of 7, but we have the smallest k, in fact, an order of magnitude less than A. And for C, we have the smallest mass. Remember, the smaller the mass, the smaller the period, the shorter the period, and our ranking is going from the longest period to the shortest period. Lastly, for D, the smaller the mass, smaller mass, but we have a large K. So small mass goes down, period goes down, large K goes up, period goes down. All right. So just kind of laying these values out here, we can start to reason through our ranking task, and we really do not need to do any calculations. Now, by all means, if you would like to, go for it. But through mathematical reasoning, we can look at these. Now, look at B. B has a large mass. Now, it's not the largest, but a large mass. The larger the mass, the greater or longer the period. And B also has a very small value for K relative to A, C, and D. The smaller the K value, the greater or longer the period. So we get our final ranking that B is greater than A, and then we can look at D and C. Let's look at C. Let's look at our extremes. Large, oh my goodness, 2,000 Newton per meter. Very large K value. Large K value means small period, short period. And then our mass is only 2 grams, so that's the smallest mass. So as mass goes down, period also goes down and gets shorter or smaller, however you want to look at it. But again, heads up, guys, these values are under the radicals, so please pay attention to that always. Question 7. We have a spring block oscillator that's showing, and you're asked to do a number of sketches and to label axes. Well, this is going to produce, our first graph is position as a function of time. And our units are going to be in meters, and of course time will be in seconds. Look at the block. It starts in A, then it goes to B, then it goes back to A, and then ultimately to C. That is the direction of the oscillatory motion. A to B, and then to C. Okay? So as you're making these graphs, it's so easy to get confused. But just think about what's happening. For each graph, pick spots where you know it's a fact. I know it's a fact that at position A, that's equilibrium. That's position equal to 0. That's our starting position. So anywhere I am at A, I am going to have to be at 0. So A, here, here, here. This is just a way to help you out. Then it's moving to B, all right? To the right to B. So it's moving to the right to B. And then from B, it's going to be moving back to the left. So think, what does it look like on a position time graph for these different motions that I've just described? So here's what we get. You get a sinusoidal graph, which shouldn't be any surprise at all. And you can see that for A's, we are passing through 0. For B, we have maximum amplitude or position, but to the right. And then for C, we have the maximum, but to the left. All right. So that is our position time. Now let's look at a velocity time. And our units, meters per second. Again, obviously seconds for time. Let's think about what's happening here at position A. At position A, this block is moving the fastest. Recall from work energy theorem that at position A, all of the spring energy, 1/2 kx squared, is converted into kinetic energy, 1/2 mv squared. So at positions D, or excuse me, there is no position D, B and C, we have a velocity of 0 for an instant. However, at position A, we have our maximum velocity. So, having said that, the last thing I want to look at before we get to this curve is that at position A, I'm either going to be up here, all right, and varying degrees, and then here, let's look at that, maximum at these varying positions. All right, so if you look at this graph, you can see that when we cross the origin, what's happening at B and C? Just what I talked about. Velocity is equal to 0 at B and C. So we are crossing the origin at those points, because underneath here, we know that the object is moving backwards. It is moving backwards. So above from A to B, yeah, it's moving to the right, but it's slowing down as the spring is extended until it stops at position B. Then it goes to the left, but is speeding up. Maximum speed A. After A, so we're right here now, guys. After A, it is moving to the left still, so we are still beneath the origin, but it is slowing down and moving to the left until it reaches 0 at position C, at which time it moves back to the right and speeds up, moving back to the right. Next graph, potential energy in joules and as a function of time. First and foremost, potential energy, energy scalar. So we're not looking at any direction. We know it's positive, so we're not going to be crossing the origin. What else do we know about energy for this spring block system? Well, we know at positions B and C, we have the maximum potential energy, 1/2 kx squared. We know at position A, we have the maximum kinetic energy, at which point all potential has been converted into kinetic, and thus we get 0 at position A because there is no more spring energy. It's all been converted into kinetic energy. So anytime we are at A, we have 0, 0, 0, 0. This helps you out, guys. It really does before you begin just sketching, because students do tend to get overwhelmed with this, and there is a lot to think about. So at positions B and at position C, we have a maximum potential energy, 1/2 kx squared. And the position x is squared. So square a negative number. You know where I'm going with this, guys. Now, let's look at our kinetic energy as a function of time, joules over time. And it's pretty much everything we just spoke about, except the opposite. So at position A, the block has the greatest kinetic energy. At positions B and C, the block stops for an instant and therefore has 0 kinetic energy. So that would be at B and C. I'll be crossing, I should touch the 0 here. And for A is maximum. Our values for velocity and 1/2 mv squared are squared. So everything is going to be above the origin here. And this graph looks very similar to the one we just did, except it is the inverse. It is the opposite. All right. So, and of course, one thing I haven't addressed yet is in between. Remember what's happening in between positions. We have a combination of kinetic energy and spring potential energy in between A and C or A and B. All right, force as a function of time, newtons over seconds. What is occurring here? Well, remember, guys, at C and B, we have our maximum force. That maximum force from the spring. Remember Hooke's law? That the force of a spring is equal to the spring force constant K multiplied by that position X. So the greater the position, the greater the force, given that the spring stays the same. So at B and C, we're going to have the greatest force. At A, all of that force has been converted into energy of motion, kinetic energy. So at A, actually, the force is zero. It's at equilibrium at that instant. So our force time graph looks like this. And I want to also take a minute to explain this. So from A to B, that force is negative and to the left. The restoring force is to the left. All right. From B to A, that's where we get the restoring force. But now what is happening to the force here? It is decreasing to zero. Okay. So we see that A to B, B back to A, 0, 0. Now what about from A to C? From A to C, we have a positive force because as soon as the block crosses over A, heading to the left, what's the spring doing? It's restoring to the right. So that's why at this instant here, we're above the origin. At C, we have the maximum force to the right. And as the block moves from C to A, moving to the right, we see that force decrease until the equilibrium, at which point it is zero, and the cycle starts over again. Acceleration, meters per second per second. Let's go ahead and look at this one. And I'm going to go ahead and tell you something. Force, the net force is equal to mass times the acceleration. We know the force of the spring is equal to the spring force constant multiplied by the position. That's Hooke's law. And anywhere we had a force of zero, we're going to have an acceleration of zero. And anywhere we had a maximum force, either left or right, we're going to have a maximum acceleration, either left or right. So this graph is the same as your force as a function of time graph for that exact reason. In question 8, we have a 2 kilogram block attached to a spring. A force of 20 newtons stretches the spring to a displacement of 50 centimeters. Now, I love this problem because this problem is really a whole bunch of problems regarding this spring block system. So let's go ahead and parcel this problem out and look at, first, let's look at A through C. So A, what is the spring force constant for this spring block oscillator? Force is equal to negative kx, that's Hooke's law. The negative sign is there because it is a restoring force. Therefore, we can solve for k because you are given both the force and the mass of the block, and you are given the displacement of the block, okay? And really for here, the mass, we're not worried about that, but we have our force and our position, which will allow you to find K. And remember, K is in the units newtons over meters. So this is our K value. And we're going to use this throughout this lengthy but fun problem. All right, B, total energy. A lot of students get tripped up here. Guys, all you're doing is you're saying, you know, what is the total energy? Well, total energy is that max extension before you let go. So really, we can find the total energy by solving for the total spring potential energy using 1/2 kx squared. The hard part's done, all right? So this is a plug and chug fest, and you can solve for your total energy to be equal to 5 joules. We're going to be using this number throughout this lengthy problem. And in C, we want the speed of the block at equilibrium. Well, after question 7, I hope you're good with the fact that this speed will be at its greatest magnitude. It'll be the greatest velocity when the object passes through the origin, because all spring potential energy, or all mechanical energy for that matter, i.e. 5 joules, is converted into energy of motion, 1/2 mv squared. So this is going to be not only the speed at equilibrium, but really the greatest speed of the block throughout its oscillatory motion. So setting 5 joules equal to 1/2 mv squared, solving for velocity, we can get that the velocity, and remember, that is the maximum velocity, is going to be 2.2 meters per second, whether it's going left or going right in its oscillatory motion. Let's look at some other fun parts of this question, D, E, and F. So in E, it says, well, what is the speed of the block at x equals 30 centimeters? So let's look at our mechanical energies that are in play here. And we want to look and set our initial equal to our final. So kinetic energies, we have the mechanical energy, we have kinetic energy, and we have the spring energy. Those are our 2 mechanical energies in this problem. So the speed at x equals 30 centimeters. Please don't forget to use units, SI units for here. We need this in meters, so 0.3 meters. Also think about what's going on in D. All right, here's 50 meters, or excuse me, 50 centimeters. So 30 centimeters would be right over here where the block's center of mass would be right around in there. And of course, here we have 0 at equilibrium. So ask yourself, how fast relative to the max speed that we solved for in part C, how fast should it be moving? Well, not as fast, right? Not as fast, because we already went through and said it was moving fastest at equilibrium. So let's set 1/2 kx squared equal to our other mechanical energies. Now be careful. Remember from unit 3, work energy theorem. Is the block moving? Yes. Is there still spring potential energy? Yes. So you're going to have both of those present in for our final mechanical energies. So initially, we have 1/2 kx squared, and we already know that that's the maximum mechanical energy for the system. We know that to be 5 joules, and so just be careful here. Solving for this with numbers, 1/2 kx squared, 1/2 kx squared, plus 1/2 mv squared, but note the position. 0.3 meters squared. And then we have our 1/2 mv squared. So algebraically rearranging this and solving for velocity, you get 1.8 meters per second. Whew. Thank goodness that is less than its maximum speed of 2.2 meters per second. So this number makes sense. Now, for E, you want the speed of the block at x equals negative 40 centimeters. So now it's over here, all right? It's over here, but maybe perhaps the center of mass of the block is there, as opposed to here when we called it at positive 30, but here it's negative. But hey guys, we're gonna go ahead and square that anyways. So we really don't need to stress out about the fact that this is at negative 40 centimeters. It's 40 centimeters to the left of equilibrium. Let's set up our expressions here. We have all spring potential, 5 joules. We know that from the beginning of this problem, part B. And then we're going to set that equal to our final mechanical energies. Is it moving? Yes. Is there a spring? Yes. So we have both spring potential and kinetic energies for our final mechanical energies in this expression. Now we're going to put in our numbers, and we already know 1/2 kx squared equals 5 joules, but I'm putting it in anyways just so you can see the equation laid out. And then we have our 0.4. It's squared, so it really ends up not mattering much. And our kinetic energy, which we're trying to solve for the velocity. So when doing this, make a prediction. Is it less than 1.8? Is it going to be less than 1.8 meters per second? Well, only a fraction of that spring has been converted into kinetic energy. Here, it's all converted at equilibrium. Here, we had, 0.2 of a meter change in position converted. Here, we only have 1/10 of that potential spring energy. So let's make a prediction that our value will be less than 1.8 meters per second. And it is. And this makes sense. If we go ahead now and look at F, the acceleration equilibrium position, now it's time to go back to those wonderful graphs in question 7 and think about it. The acceleration at equilibrium. Well, remember the force at equilibrium is 0. If the force is equal to 0, then the acceleration is also equal to 0. And we went through a very lengthy intuition of that fact in the preceding problem. So force, Newton's second law, is equal to mass times acceleration, but the acceleration is 0, or we can set that to kx squared is another way to look at it. What is the position at equilibrium? The position at equilibrium is x equals 0, and we know force equals mass times acceleration, and force also equals the spring force constant multiplied by the position. Negative sign there is indicative of this being a restoring force. So this gives you an answer of 0. 0 meters per second, and question 8 continues on. Parts G, H, and I. Find the magnitude of the acceleration at x equals 50 centimeters. Magnitude of the acceleration right here. What do we know about that? We know we have our greatest acceleration. We have our greatest force, and this force is to the left, and this acceleration is to the left. However, this question says magnitude, so we're not concerned with signage. We're not concerned with the direction of this vector. We're concerned with the magnitude only. So let's go ahead and solve part G. Using Hooke's law, we can set the force as equal to the spring force constant multiplied by the position. We know Newton's second law that the force is equal to mass times acceleration. Therefore, mass times acceleration is equal to Hooke's law. And with that, we can solve for the acceleration or the magnitude of the acceleration. We know K, we found that. We're given the position at 0.5 meters. And we also know the mass of the block. So it comes into play. We are able to find the acceleration at x equals 50 to be 10 meters per second. And again, that's the magnitude of the acceleration. Part H, let's find the net force on the block at the equilibrium position. Well, the net force on the block at the equilibrium position. Let's use Hooke's law. And remember, at the equilibrium position, x is equal to 0. So for that reason, the force is equal to 0. And along that same line of logic, we knew that the acceleration was equal to 0 at the equilibrium. If the acceleration equals 0 at the equilibrium position, so does the force, guys. So both the force and the acceleration are 0 at the equilibrium position. Part I, let's find the net force at x equals 25 centimeters, or 0.25 meters, which is right in that halfway mark, right in the halfway. So force is equal to spring force constant multiplied by the position. Let's go ahead and solve this equation to find the force is equal to negative 10 newtons. So if the block is over in this position here, the force is to the left, the acceleration vector to the left. All right. And in this case here, you are being asked for the net force. So it is appropriate to use signage, either a negative sign or to the left, to show that that's where the force is. And as this problem continues to part J, we're almost there, guys. The position where the kinetic energy is equal to the potential energy. So we want to look at kinetic energy equal to potential energy. Let's go ahead and look at this graph. I want you to look at what's going on here. We have the amplitude, which is the position. So this would be max position right. This would be max position to the left. 0 position is equilibrium. And we have the kinetic energy in blue, and the dashed red line represents potential energy. All right. We know at the equilibrium position, we have maximum kinetic energy. So it's moving the fastest. And at that point, we have 0 potential energy. In this case, there's 0 spring potential energy at the equilibrium. It's all been converted into kinetic energy, 1/2 mv squared. All right. So this graph is really cool because not only can we look at symmetry, but we can look at these areas here where they intersect, and those areas are where kinetic energy equals potential energy. And here's what's so cool. Hey, it's not at x equals 0.25. It's not halfway through. All right. If you follow this line straight down, I wanted to redo that because that was horrible. Follow this line straight down here. That's not the middle. So we've been doing this long enough, guys. You should know that we are looking at potential energy, but then we're looking at the kinetic energy where the velocity is squared. Hey, sweetie, come say hello to my students. Come here. Yeah, say hi.
Hi.
All right, in the final part of question 8, you are asked to find the position where the kinetic energy is equal to the potential energy. And you want to put some thought into this, and this particular part of this question often confuses students. So I want to consider this graphically for a moment. Here we have potential and kinetic energies. Down here, we have our displacement. Now, the positive capital A means that positive max amplitude or position. So that's what those are showing. The blue line is the kinetic energy, 1/2 mv squared, and the dashed line is potential energy, in this case, spring potential energy, 1/2 kx squared. So we are looking for the position where these two are equal. So this is really cool to look at. Find here, now we had a maximum, this is the maximum kinetic energy. 0 is equilibrium, x equals 0, and we've already been through that repeatedly to understand that's maximum kinetic. And at that same location, we have 0 spring potential energy because it's all been converted into kinetic energy. Our maximum energy here is 5 joules for the system. We calculated that earlier on in this problem. And so I'm going to come right here to half, okay? And I want you to notice what's special about that location. At 2.5 joules of energy, we see that the kinetic energy graph and the potential energy graph intersect, which means they are identical at that point. Now, what's even more fascinating is if we come down here to the position. Let's look at this amplitude, this position, and that is not at a position where x equals 0.25, which is what many students believe to be true. Oh, at that position, it must be equal to 0.25. If my maximum x position is 0.5, then it must be halfway. And that is not true. Let's look at why. In part J, half of our energy total was 2.5. So if we set 2.5 equal to the spring potential energy and solve for x, we're going to find that it is not halfway. It is not 50 divided by 2 is 25 centimeters. Therefore, 0.25 meters must be that position. That is incorrect. And I hope you can see why. We have this in joules, and we're going to be solving for x, and x is squared. So it's an exponential relationship. So we're going to be taking the square root ultimately to solve for x. That should make some sense after coming this far through the course when we look at this. This position is squared, and we're trying to compare it to the amount of energy. Solving this for position, we're going to find that the position is not 0.25, but rather 0.35. It's further over this way. If this was halfway, which I believe according to this problem was 25 centimeters, half of 50. That's not the case. Again, I love this particular part of this problem. In fact, I just love question 8 in general. So our answer is not what many students predict to be at 25 centimeters. Rather, it is at 35 centimeters, and it is because of this exponential relationship between the position and the total energy. Moving on to question 9, we have a cart of mass 0.5 kilograms, and it is attached to a spring, and the spring constant is given to you in the problem. It's a frictionless air track. We have one of these in lab, remind me, and I'll get it out. The cart is stretched 10 centimeters from equilibrium and released from rest. Calculate the maximum speed of the cart. Well, here's what these air track systems look like. And so just to get an idea, let's look at position A. Position A, we have our maximum potential energy. That's our maximum spring potential energy, 1/2 kx squared. So we see here on these bar graphs, there is 0 kinetic energy at that moment. It's not moving. There's all potential energy, 1/2 kx squared, where our x value is at its maximum. And then TME is the total mechanical energy. Now look at the total mechanical energy throughout positions A through E, and you'll see it remains constant. It's the same. And the reason for that, you understand, I hope, is that as potential energy is converted, it's converted into another form of mechanical energy, in this case, called kinetic energy. So position B, we have a mixture of potential and potential and kinetic energies. We have 1/2 mv squared, and we have 1/2 kx squared. At position C, that is where all of the spring potential energy is converted into energy of motion. So at position C, this cart will have its greatest speed because all 1/2 kx squared has been converted into 1/2 mv squared. And then we see position D is the same as position B, where we have a mixture of energies. And then, of course, at E, we are back to where we were at A, where we have maximum potential energy. And for that instant, the cart is not moving. All right, so lengthy intuition there for question 9. That's okay. Now let's solve it. We have our initial mechanical energies, and we'll set those equal to our final mechanical energies. Our total mechanical energy in this system is when the spring has its maximum extension or compression. So that is 1/2 kx squared, and we can set that equal to 1/2 mv squared because we know that this cart will have its greatest maximum speed as it passes through the equilibrium. And at that position, all of our spring energy is converted into kinetic energy. So now we can solve this problem. We know K, we were given that. We have our stretched maximum position of 10 centimeters, but we need to put that into meters, 0.1, and it's squared. Set that equal to 1/2 mv squared. Solving for the velocity, which we now know will be the maximum speed, is 0.77 meters per second. Question 10. You're asked to draw a free body diagram for a mass hanging vertically on a spring at its equilibrium position and sum the forces for that scenario. So as you can see here from this little schematic, we have an unstretched spring. A block of mass M is added to the spring. The spring extends, comes to rest at what we will call its equilibrium position, and has a change in length of the spring. At this position, if we sum the forces vertically, we see here that the force of the spring upward is equal in magnitude, opposite in direction to the force of gravity. If we sum the forces here, we can show those equal 0 because it's not accelerating vertically, so they are equal and opposite. Now, one step further, the force of the spring is equal to Ky. Now, you might be asking, where's y coming from? Well, recall from our study of kinematics that we're considering the vertical direction, we replace x with y. So this is Hooke's law. Also, notice I have neglected to put in the negative sign. That's because by this point you understand that the negative sign is there because this is a restoring force. So, if the force of the spring is equal to the force of gravity and the force of the spring is equal to the spring constant multiplied by its vertical position, then we get this expression, and therefore we can show the relationship that the Ky is equal to mg, or mass gravity, force of the spring equals force of gravity, and that is where I wanted to go with question 10. In question 11, we're going to use and build upon what we did in question 10. So let's get to it. A block of mass 1.5 kilograms is attached to the end of a vertical spring. You're given the spring constant. After the block comes to rest, it is pulled down a distance of 2 centimeters and released. So it's resting, and then it is pulled an additional 2 centimeters down and released. Find the frequency of the oscillations, and part B, maximum and minimum amounts of stretch. So in the preceding facts for these problems, you're basically looking at the equilibrium position and using the summation of the forces vertically that we went through in question 10 to ultimately be able to figure out what is the maximum from equilibrium, both up and down. So let's answer part A and look at the frequency, the inverse of 2 pi, and that multiplied by the square root of the spring force constant divided by mass. Part 1 is a plug and chug. We get 2.25 hertz, or the inverse of a second, for part A. For part B, we need to use some additional information. Now, recall in question 10, we showed this to be true by summing the forces vertically. Well, if we divide both sides by the spring force constant K, we can solve for that vertical position. And the vertical position in this case, which is 15 newtons divided by the spring force constant of 300 newton per meter, gives us a vertical position of 0.05 meters, which is 5 centimeters. Now, recall in this question, from equilibrium, it is pulled down an additional 2 centimeters. Well, 5 plus 2 is going to give you your maximum of 7 centimeters for the extension, and for the compression, when it goes the other way up, 5 minus 2 is 3 centimeters for the minimum amount of stretch. In question 12, we have a 2 kilogram block. It's attached to an unstretched spring. You have the K value, and released from rest. Determine the period of the block's oscillation and find the maximum and minimum displacements of the block from its equilibrium position while undergoing simple harmonic motion. Well, for the period, we're going to use our equation. 2 pi is equal to the square root of mass divided by K. That's a plug and chug. The period is 0.63 seconds. Part B, we need to find the maximum and minimum displacement from equilibrium. Well, from question 10 and 11, we've shown from the vertical summation this to be true. Dividing both sides by K allows us to be able to find the vertical position, and by doing so, we can find the vertical position to be equal to 0.1 meters or 10 centimeters, which is the displacement of the block from equilibrium when it is released from up top. In this question, it's released from the top. In the previous question 11, it was brought to equilibrium and then stretched an additional 2 centimeters down. So take a look at 11 and 12 again. Make sure you understand the difference between the two. In question 13, you're asked to sketch a pendulum of mass m, length L, at an angle theta from its equilibrium position, and draw the free body diagram for this pendulum, and use your free body diagram to show what is the restoring force of the pendulum when it is in simple harmonic motion. This schematic represents this scenario well. So we've been studying pendulums since our Unit 2 dynamics. So we have our L, theta. Here is the bob, or the mass on the string, and force of tension. And again, look, the force of gravity is straight down toward planet Earth, as indicated and marked mg here. And then we have our resolved vectors also on this schematic. So here we can show the force of tension to be equal in magnitude, opposite in direction to mass gravity cosine theta, where this angle theta is equal to the angle of theta displaced from the vertical. Look at the geometry, play around with the right triangles a little bit there, and you'll see these angles are identical, which means that this particular side of our right triangle is the adjacent side, and we know the hypotenuse to be force of gravity, which means we can solve for this component to be mg cosine theta. Likewise, we can show the restoring force to be equal to the opposite of theta, or mg sine theta, which is shown on this schematic as a blue arrow. It is mg sine theta that is the restoring force of a pendulum in simple harmonic motion. Now, take a look at this schematic, which I found online at a website called the Physics Classroom, which has a lot of awesome animations. Well, I like this one a lot because it's showing at the different stages of simple harmonic motion how force of tension relates to the perpendicular, the mg cosine, as well as that restoring force, which is mg sine theta. Now notice the restoring force is 0 at equilibrium, just as we've explored in spring block oscillators. At this instant, the object, the plumb bob, is moving with its greatest speed because all of that gravitational potential energy has been converted into kinetic energy. However, at the two extremes here, we have our greatest restoring force. This should sound familiar. It's the same thing as when we looked at spring block oscillators. So on either extreme position, we have our greatest restoring forces. In the middle, at equilibrium, we have a force of 0, therefore the acceleration tangential is also 0. I have to be careful there because there is a force acting on this object. And so that's a good representation of what's going on to really understand the motion of an object, of a pendulum in simple harmonic motion. Also, what I had to be careful there, I want you to look at the force of tension. All right? Force of tension at the equilibrium position, the force of tension is actually greater than the force of gravity. That is because this object is being manipulated into a circular path by a center-seeking force. So there is a centripetal or inward acceleration occurring here. And that's very important to at least mention for this particular problem. So in question 14, we have a simple pendulum that has a period of 1 second on Earth. You are asked, what would the period be on the moon, where gravity is 6 times smaller than that on Earth? And then you are also asked to calculate a new length for the pendulum that would compensate for this difference in gravity, returning the period to 1 second. Okay, so let's look at our equation here for the period of a pendulum is equal to 2 pi multiplied by the square root of the length divided by the acceleration due to gravity. Here is an animation to help you conceptualize this problem. As you can see, the pendulum with the greatest length, the black pendulum, has the greatest period. In other words, it takes the longest amount of time to complete a cycle. Now, look at the blue pendulum. The blue pendulum has the smallest length. And if you look at our equation, as length goes down, the period also goes down. Now, of course, length is under the radical. You need to be aware of that. So this will help you to kind of think about this problem here. In this problem, we are also going to be changing the value for the acceleration due to gravity. It's going to be 6 times less. But again, that 6 times less is in the denominator under the radical. So let's go ahead and look at how this would be. The period of a pendulum is inversely proportional to the acceleration due to gravity, which is under the radical, square root of little g. So the period of the moon we can find to be going up by the square root of 6. Again, let's look at it. As the value in the denominator goes down, the period goes up. So we're going to be increasing the period by the square root of 6. That gives you an answer of 2.4 seconds. So this pendulum on the moon would take 2.4 seconds to complete a cycle. Now, in the next part, we want to return the length. We want to determine the new length in order to compensate for this difference in gravity. Well, we know on planet Earth the period. That was told us in the problem, it's 1 second. So we can set 1 second equal to 2 pi, the square root of the length divided by the acceleration due to gravity on planet Earth. We're using 10 meters per second there. We can then look at how this is proportional. So as the period of a pendulum will go up as the length goes up. So it is directly proportional to the square root of the length. As one goes up, the other goes up. So what we're going to need to do is find a new length, and that new length should be less than what it is on Earth. Okay? Remember in the beginning of this problem, we had 3 pendulums. Recall that the pendulum with the smaller length had a shorter period and a higher frequency. Let's go ahead and calculate the length of this pendulum on planet Earth. That is equal to 0.25 meters. Now, in order to finalize this problem, we know we're going to get a smaller length, and that smaller length will result in a decreased frequency, decreased period and increased frequency, which will compensate for the decreased value for gravity on the moon. In other words, we need to ensure that we are satisfying this fraction here, where we have the length divided by the acceleration due to gravity. Well, here's our length, and we know that our length is going to be decreased by the square root of 6. So we're going to divide this length by the square root of 6. By doing that, that allows us to calculate for the new length, which is found to be 0.10 meters. So if we decrease the length from 0.25 meters to 0.1 meter, we can return the period of this pendulum back to 1 second on the moon, where the acceleration due to gravity is 6 times less than that on Earth. All right. So, question 15. A grandfather clock is designed such that each swing of the pendulum takes 1 second. Each swing takes 1 second. This is actually has a special name. It's called a seconds pendulum, intuitively. So this is a seconds pendulum. What that means is each swing takes a second, so the period is not 1 second, but 2 seconds. So each swing, 1 second, 1 times 2 gives us the period of 2 seconds. How long is the pendulum of a grandfather clock? Period of the pendulum, again, 2 pi and the square root of the length divided by little g. So after going through question 14, I've been over this repeatedly, and you should have a really good mathematical understanding for how both the length and the acceleration due to gravity will change the period, the amount of time for a cycle. All right, so looking at this, we have 2 seconds is the period, 1 second each way, 2 seconds for the entire cycle, equal to our constant here, 2 pi, square root length, and we know little g, 10 meters per second, so we can now mathematically solve for the length, and the length of this pendulum is 1 meter. Now, of course, we're using 10 meters per second in our problems, but for a true seconds pendulum using 9.81, you will get a smaller value, 0.94 seconds or something like that. But for all practical purposes, right around, and I said seconds, I meant 0.94 meters, right around 1 meter is the length of the pendulum for a seconds pendulum, this grandfather clock. Question 16 is another ranking task, except this time instead of ranking spring block harmonic oscillators, we're ranking pendulums in simple harmonic motion. And we're going from highest to lowest frequency. You know, I always circle that. Uniform mass density is telling you that they all have that same amount of mass per volume. However, hey guys, mass doesn't matter, does it? So you're not falling for that. So you can look at this ranking task and immediately neglect the fact that these all have that the mass of plumb bob B is greater than the mass of plumb bob D. Who cares? Because mass is irrelevant. Mass isn't even in the expression. You've seen this one from a couple problems ago, looking at how the length of the string affects the period or the amount of time for a cycle. And we've been over a number of these problems. So you can see mathematically that the frequency is directly proportional to little g, but inversely proportional to the square root of L. And the square root of little g is directly proportional. But you see that it's under the radical. I've said that half a dozen times already. So as the length goes up, the frequency goes down. All right. Now, again, it's under a radical. I feel like I must always say that. All right. So in this animation, we see the blue pendulum has a greater frequency. Has a greater frequency because it has a smaller length. And we want to go from highest to lowest frequency in this problem. So let's start just looking at the length because little g is the same for all of them. 2 pi, or the inverse thereof, is a constant. So all we are straight up looking at is how frequency is inversely related to the square root of the length. Now, that enables us to rank these because we see the highest frequency is the one with the shortest string, D, and then the next one, A, and then next, B, and then finally C has the longest length. And because it has the longest length, it has the lowest frequency. All right, so this number goes up and this number frequency goes down. And that's what we see for C, is that because it has the greatest length, it has the lowest frequency. DA, B, C is your ranking from highest to lowest frequencies. Here we have 6 figures, and they show metal spheres hung on the ends of strings. And these spheres have been pulled to the side and released, and they're swinging back and forth in simple harmonic motion. For each sphere, you are given diagrams that show the mass of the sphere. Are we falling for that, guys? No, it's independent of mass. Mass doesn't matter. The frequency of the string, okay, and how far in terms of the angle from the vertical, okay? Well, the angle theta from the vertical, This is something known as the small angle approximation. The angle above deviation, the angle from the vertical for a pendulum in simple harmonic motion is independent of period and frequency. And it's a similar intuition that I went over earlier with the amplitude of a spring block oscillator, where I showed you a tautochrone, a cycloid, and we talked about how amplitude was independent of the period and frequency. It's very similar here. However, there's a caveat. It's only true for small angles. Now, that's really not relevant in this course, but if you continue your studies of physics, you'll look at this extensively. However, for our purposes, we don't need to pay any mind other than all of these angles of theta are small. However, independent and not going to be a factor for this ranking task whatsoever. Okay, so, and lastly, we're going to rank on the basis of the length of the string. And in the last problem, we went over the fact that the frequency of a pendulum in simple harmonic motion is equal to the square root, or the inverse of 2 pi, and that quantity multiplied by the square root of little g over L, where L is the length of the pendulum. We've also gone over this. Frequency is inversely related to the square root of the length of the pendulum. So if you've been viewing this podcast for some of the previous problems, we've been going over this for each one. So we can rank these quite simply. Let's look at E is equal to F. E, all right, theta, don't need to worry about mass, doesn't matter. And then, so now we're looking at frequency. Well, these have the smallest frequency, which means they have the longest length. Okay? D and B. D and B, we're looking at 0.6 hertz and 0.6 hertz. Frequency is going up. Well, they're inversely related. So as frequency is going up, the length must be going down or getting shorter. And lastly, we have our 0.75 hertz. So that is our greatest frequency and thus our shortest length of string. Question 18. The period of an ideal pendulum is T. Now, that term ideal, you guys, if you heard me talk in the last couple problems, I mentioned the small angle approximation. So in larger angles, pendulums do not exhibit simple harmonic motion like we are studying them. Okay, we're studying what's termed ideal pendulums. So that's important, at least for me to mention in this course of T. If the mass of the pendulum is tripled, all right, we're about to do some of this, and the length is quadrupled. What is the new period, T, of the pendulum expressed in terms of T? Semi-quantitative reasoning, mathematical reasoning, here we go. Period, here's our equation for period that we've been using. Period is directly proportional to the square root of the length and inversely proportional to the square root of little g. Let's make up numbers to help conceptualize this problem. All right, so we have our length of L, and so our length of L is quadrupled, and period is equal to the square root of the length, and the square root of 4 is 2. So that helps. Then what this means is if we have 2t, and we know that that's the only factor in this one, because mass does not matter. So you get the point now. You would think mass matters. Mass is not a factor. It is independent of mass. So the fact that the mass is tripled doesn't matter. But the fact that the length is quadrupled, oh yeah, that matters. And so by quadrupling, the square root of 4 gives us 2, which means the period is now twice as long. It takes twice as long to complete a cycle. Question 19. A pendulum of length 20 centimeters and mass 1 kilogram is displaced an angle of 10 degrees from the vertical. What is the maximum speed of the pendulum? Maximum speed of the pendulum. I bet you already know that the maximum speed of that pendulum will occur as it swings back through equilibrium. As it swings back through equilibrium, all of the gravitational potential energy is converted into kinetic energy. So if we solve 1/2 mv squared for v, we can find the magnitude of the velocity or the speed for this pendulum. Also, look at the variables you are given. And we've been talking about this long enough. We've gone through the fact that the height is equal to L minus L cosine theta. And if you factor out the L, you get L multiplied by the quantity 1 minus cosine theta is equal to delta y, or height. That's nothing new. Let's set up our energy expression and put our initial energies, which are the gravitational potential energies, and set those equal to our final mechanical energy, which in this case is the kinetic energy, 1/2 mv squared. We know that's going to be where the maximum speed of the pendulum occurs, is as it swings through equilibrium. Let's put in our h value. Also, mass does not matter. So we can go ahead and put this in. And I said mass doesn't matter. So we can take out the mass. And let's go ahead now and solve this expression. Be careful with your algebra, please. Take your time. Make sure you don't make any careless errors. And solving, multiplying both sides by 2 and taking the square root of this quantity will give us the maximum speed of the pendulum, which occurs as it swings back through the equilibrium position and is 0.25 meters per second at that position. Now, in question 20, a pendulum of length 0.5 meters and mass 5 kilograms is displaced an angle of 14 degrees from the vertical. What is the speed of the pendulum when its angle from the vertical is 7 degrees? This is a great question. I love this question. If you viewed the video solution for question 19, that was kind of a building up to this one. All right. We know the max speed occurs as position swings back through the equilibrium position, but what about in between? In fact, what about halfway? Now, you know by this point, be careful. Halfway, what are we comparing? You're looking, is there anything under a radical? Is there anything squared? This is critical information. So our mechanical energy is equal to our final mechanical energy. Initial equals final. So let's set up our energy argument and expression where we are starting off with this gravitational potential energy. You already know that when expressing H for a pendulum in terms of L and theta, we're going to use L minus L cosine theta, which is equal to the height, which will allow us to use the gravitational potential energy as our total mechanical energy. And we can set that then equal to our final mechanical energies, plural. In the last problem, we just had the kinetic 1/2 mv squared. Not in this problem. In this problem, we have 2 energies. Ask yourself, is the pendulum moving? Yes. Is the pendulum, does the pendulum have gravitational potential energy relative to a defined zero line? And the answer is yes. In question 19, our zero line was at that equilibrium position, but now it is above that equilibrium position. So we have two different mechanical energies in this final expression. So solving for these quantities and recognizing that mass is in each portion of the expression, so therefore we can cancel out mass. Mass doesn't matter. We get the following, kind of a little bit of mess of algebra. Rearranging this, I've given some intermediate steps here. A lot of students have asked me to give intermediate steps and numbers because they get lost if I just go to the answer algebraically. So we get these quantities, and then lastly, multiplying both sides by 2, taking the square root, we can solve for the velocity to be equal to 0.47 meters per second. So what is its greatest speed? It occurs as it swings through equilibrium. All right, 0.4 seconds is the velocity at 7 degrees. Now, if you solve this same problem for maximum speed, you get about 0.545 or something meters per second if you solve for the maximum speed. Yet halfway through its delta theta, okay, from 14 to 7, it's already moving 0.47 meters per second. That is because we have a term here, velocity, and that velocity is squared. So as I've urged you throughout the course, be careful, because it would be so tempting to say, well, if the maximum speed is 0.545 or whatever it really is, it's somewhere around in there, then at angle 7, it must be 1/2 of that. That's not true at all, because velocity is squared. And to solve for the velocity, we are taking the square root of the quantity. And that's going to give us our final answer. As always, be careful, guys. Question 21. A pendulum is released from rest at the start position on the diagram shown, and it oscillates in simple harmonic motion through positions A, B, C, and D. The gravitational field strength on the surface of Jupiter is 26 newtons per kilogram, and on the moon, 1.6 newtons per kilogram. Rank the pendulum's period on these two planets and Earth. Okay? Recall from the universal law of gravitation that, that the acceleration due to gravity, which we're going to use 10 meters per second on planet Earth, is the same as the gravitational field strength as 10 newtons per kilogram. Look at the actual SI units there. They simplify to meters per second. So I just wanted to remind you of that because that was a couple units ago when we talked about that. So let's go ahead and rank the period here for these pendulums. The expression 2 pi multiplied by the square root of length divided by the acceleration due to gravity. All right, so as the period will increase as the length of the string will increase. We've gone over this repeatedly. As the acceleration due to gravity increases, like it is on Jupiter, the period will decrease. All right, the period will get smaller and smaller and smaller, which means the frequency gets larger and larger and larger. So our ranking for these, given that the period is directly proportional to the inverse of little g, the acceleration due to gravity squared, or I could call this the gravitational field strength, and I just said squared, I meant under the radical square root. Okay, so we've looked at this. This should make our ranking task easy, saying that the period, the amount of time to complete a cycle on the moon, is greater than that on the Earth, which is greater than that on a planet Jupiter. And you can see this directly relating to the fact that the gravitational field strength, who has the least? Which planet? The moon. Which one has the greatest? Jupiter. In between, that'd be planet Earth. And we see that right here mathematically. All right, question 22. A wave is traveling on a rope and it has a frequency of 2.5 hertz. If the speed of the wave is found to be 1.5 meters per second, what are its period and wavelength? Okay, so we have a diagram here that is showing you the wavelength. The wavelength is considered to be a cycle, or 2 pi r, and we also have an animation here that's pretty cool showing a transverse wave. So preceding question 22 were a series of facts about waves. So recall that a wave is a repeated disturbance carrying energy through a medium. So there's two things you need to be thinking about for the next several problems. What type of wave is it? What is going on in the medium? And how is the wave traveling with respect to the medium? So this animation proves to be very helpful. So as you can see, the energy is propagating from left to right. However, notice these red points along the line. These red points are moving up and down. That is a property of a transverse wave. So as the wave moves left to right, a particle, a point on the medium, is moving at a 90-degree angle to the propagation of the energy. In other words, up and down. It is not moving left and right. That is very important. So take a few minutes and really look at this animation to understand the difference between the propagation of the energy and the movement of the medium. All right, now let's get to this problem. This is fairly straightforward here. We have the formula for a period. A period is the inverse of a frequency, and we've been talking about that now for several units. And so we can take 1 divided by 2.5 hertz given in the problem to calculate the period to be 0.4 seconds. Okay, and that again is the amount of time to complete a full cycle. Now, the velocity of a wave is found to be 1.5 meters per second. And our equation that we're using, we set velocity is going to be equal to the wavelength multiplied by the frequency. And I would always encourage you guys to look at your SI units here. So we have meters per second, and that should be equal to the wavelength, which is measured in meters, multiplied by the frequency, which is the inverse of a second. And as you can see, we get meters per second. So 1.5 equals lambda, or the wavelength, multiplied by our frequency, 2.5 hertz. So we can find that the wavelength in this problem is 0.6 meters. In question number 23, the period of a traveling wave is 0.5 seconds. Its amplitude is 10 centimeters, and its wavelength is 0.4 meters. What are the frequency and the speed of this wave? Again, I have a schematic showing a transverse wave, a wave in which the propagation of energy or the disturbance through the medium is moving from left to right. However, the medium itself is moving directly up and down. So, recall in the preceding facts that the energy carried by a wave is dependent on its amplitude. So if we increase the amplitude, we are increasing the amount of energy. Of course, you now know The period is the amount of time to complete a cycle, a full wavelength, 2 pi r. And the period and the frequency are inversely related to one another. Again, we've been talking about that for several units now. Let's calculate the frequency, which is the inverse of a second, and you're given the period. So 1 divided by 0.25, you get an answer of 2 hertz, or the inverse of a second. And for velocity, again, looking at our equation, it's equal to the wavelength multiplied by the frequency. We can simply plug in our numbers to calculate the speed of this wave to be 0.8 meters per second. All right, question 24. A horizontal rope with a linear mass density equal to 0.5 kilograms per meter sustains a tension force of 60 newtons. The non-attached end is oscillated vertically with a frequency of 4 hertz. You're asked, what are the speed and wavelength of the resulting wave? And in part B, you're asked, how would the answer to these questions change if the frequency were increased from 4 hertz to 5 hertz? Let's take a look here at these 2 wave rules which were in the preceding facts. First, the speed of a wave is determined by the type of wave and the characteristics of the medium, not by the frequency. And wave rule number 2, when a wave goes into a new medium, its speed changes, therefore its wavelength changes. However, frequency, again, does not change. Now let's look at the schematic diagram here. And if we have not gotten to this lab yet, this is exactly what we're going to be doing. It's one of my favorite labs. So we have a string oscillator here, and it's coming over to a modified Atwood machine. So we have a pulley on the side of the bench and a hanging mass. Now we can take that hanging mass and manipulate the force of tension, and therefore we can manipulate the overall velocity of the wave. So it's a really cool lab. I also want you to look at the length here. We have the length of the string denoted with a capital L. And of course, as you know, a wavelength, if I were to mark a wavelength here, it would be from this red dot to this red dot, being a full cycle. All right, so now let's look at our new equation. So velocity is equal to the square root of the force of tension divided by mu. Mu is the linear mass density given in this problem. Mu is in SI units of kilograms per meter. So in this problem, you're given mu to be 0.5 kilograms per meter. In this lab, you're going to determine this experimentally. Now we can plug this into our new equation where we're dividing 60 newtons by the linear mass density, or mu, taking the square root of that to calculate the velocity. Velocity is equal to 11 meters per second. So that is the speed of this wave as it propagates through the medium, which is the string. Again, a point on this string would move vertically up and down, whereas the disturbance or energy would propagate from left to right, right to left. Okay? So we have this. Let's calculate the wavelength, or lambda, using our wave equation where the velocity is equal to lambda multiplied by the frequency. We can set 11 meters per second equal to wavelength and frequency. Dividing both sides by the frequency gives us lambda. So the distance of a wavelength, for example, in this schematic from one red dot to another red dot, is 2.8 meters. So that is our value for the wavelength for part A, given a speed of 11 meters per second. And in part B, we're now going to analyze this same question. However, the frequency is increased. So we're being asked, how would the velocity and the wavelength change if frequency were increased from 4 to 5 hertz? Okay, So we have our equations here that we've been using. We can go ahead and set up an expression here. Let me tell you what I did in case you don't see this. Velocity is equal to the square root of force of tension divided by mu. Velocity is equal to lambda multiplied by frequency, wavelength by frequency. So I have taken wavelength and frequency and substituted it into this equation. The next thing I want you to look at are the values under the radical. We have 60 newtons, that did not change, and we also have the linear mass density of this string, which is a property of this string, that did not change. Therefore, the speed does not change, because the velocity is equal to the square root of the force of tension, which didn't change, divided by mu, which did not change. So our speed is not going to change. It's still going to be equal to 11 meters per second. And in order to satisfy that, we need to have a wavelength that is decreased. And we've seen this, guys. We've seen this. Frequency goes up, wavelength goes down if velocity remains the same, which in this case it does. So speed is the same, wavelength is reduced from 2.8 meters per second to 2.2 meters per second. In question 25, two ropes of unequal linear mass densities are connected. A pulse is created in the rope on the left. It propagates to the right toward the interface with a heavier rope. In other words, a rope with a greater linear mass density. How do the speed and wavelength of the incident pulse compare to the speed and wavelength of the transmitted pulse? How does it compare to the reflected pulse? A lot of terminology here, guys. So in the preceding facts before question 25, I'm throwing a lot of terms at you. I want you to go back into the problem set, read back through all those facts, make sure you're good with all the terminology being used in this question here. So we're going to look at this from a semi-quantitative perspective. So we're going to use our equations. We're going to look at the fact that the velocity is proportional to the inverse of mu. And again, mu is under the radical. So that's important to consider. Going back again and looking at this value as mu goes up, velocity goes down. As mu goes down, the speed increases, velocity goes up. We have our go-to wave equation, lambda and frequency, and now we have a very useful animation. I want you to look at this animation. This is the answer to the question. So for this problem, we're going to compare the pulse that is, the incident pulse is here. This is the transmitted pulse. This is the reflected pulse. Again, incident, transmitted, incident, reflected. So part of this incident pulse is transmitted, part is reflected. Now, when a pulse enters a new interface at the wave boundary or the pulse boundary, if that new medium is denser, the pulse that reflects is inverted. In this case, it's entering a more dense medium, so our reflected pulse is inverted. Now, I want you to only consider the reflected pulse. The reflected pulse here, what do we notice about it? Number one, its amplitude is less than the incident pulse. Number two, its speed appears to be the same. Now that is true. The speed is the same. Frequency is not changing. Wavelength is not changing. The medium is not changing. It's the same medium, that less dense medium. So it's going to have the exact same speed. It's going to have a decreased amplitude. And it's also, if it has the same velocity, frequency doesn't change. What about wavelength? It's the same as well. Okay? Now, let's go ahead and look at the transmitted pulse. The pulse entering the denser medium. The pulse entering the denser medium appears to be moving slower, and indeed it is. Its velocity has decreased. We can look at this mathematically here. As mu goes up, speed goes down. So that's intuitive, I would hope. And again, we can look at this as it is inverse. They are inversely related to one another. So that makes sense. Mu did go up. The speed does go down. Now let's look at the amplitude. The amplitude, the energy, the height of this wave. It appears to go down. And indeed it does. The energy is constant throughout. The frequency is constant throughout. Well, the initial energy in the incident pulse is now split between a transmitted pulse and a reflected pulse. Now, the sum of those energies are the same. So not only do we see the reflected pulse amplitude decrease, we also see the transmitted pulse amplitude decrease as well. Okay? Now, velocity decreased. What about wavelength? What about wavelength of the transmitted pulse? Now, the reflected pulse we said was the same because the speed was the same. Frequency didn't change. Lambda must be the same. But what about for the transmitted pulse? You can see from this animation the wavelength has decreased. Again, mathematically, guys, look. If this goes down and this stays the same, then this must also go down. So the wavelength is smaller for the transmitted pulse. A lot to look at and think about in this problem. So pause the podcast, read through this answer, view the animation as much as you need to, and then I want you to ask yourself something, guys. What if this same incident pulse entered a medium that was less dense? How would that change? What if this were fixed at one end? How would these answers change? And so there's a lot to think about in this problem with these concepts. Question 26. Wave pulses travel toward each other along a string, as shown below. Answer the following questions in terms of the resulting superposition of the pulses when their centers are aligned. We're going to rank these based on the maximum amplitude of the resulting superposition. Okay, so we're looking at constructive and destructive interference. And in B, we're going to rank the magnitude. You know I'm going to underline that. Magnitude of the maximum amplitude of the resulting superposition. Okay, so they're heading toward one another. Let's look at A. So this wave's going this way. They're going to interfere with one another, in this case, constructively. So we're going to expect or predict an increased amplitude. Now let's look at B. Again, remember, I'm not going to do this for all of them, but they are heading toward one another. They will interfere with each other. And in this case here, we're going to have some destructive interference. Okay? Destructive interference resulting in a decreased amplitude. In C, heading toward one another, and again, they're going to interfere. We're going to see destructive interference, and we can predict that our amplitude is going to be beneath the origin here. So we're going to end up with a wave something like this, okay? but it will be underneath. And here they're going to interfere constructively, so we're going to end up with a very large amplitude here, inverted. So, ranking these guys here, for part A, rank maximum amplitude. So, D is the smallest. Again, we're not looking at magnitude, so notice this is negative. Okay, so this resulting wave is going to be something like, like this. It's going to be considerably, as far as the signage, it's going to be the most negative. So that's why we have that as the smallest. And then we go to C, which we talked about would possibly be something like that once these interfered with one another. Then we go to B. Okay, B, we're going to have something perhaps that looks like this, but it's going to have a positive value, which is why it's greater than C and D. And then lastly, our largest resulting superposition is going to be A, because where these, it's basically going to be what we saw in D, except a positive value, something like this. You get the point. All right, so now let's look at B, magnitude of the maximum. Well, if we're only looking at magnitude and we're not concerned with the sign, the signage, then if that's the case, you can see A and B or A and D are going to be the same magnitude, and so will C and B. So from smallest to largest, B is equal to C. Again, magnitude. And A is equal to D, because we're only considering the magnitude, whereas in part A of this question, we were also considering a positive or negative value. Okay, so for closing on this one, big difference here. We're looking at constructive and destructive interference, and that is known as wave superposition. And we've been able to rank these both, including the positive and negative, the signage, and also rank these based on the magnitude. In question 27, you were asked to complete the wave superposition supplement that was given to you in class and is also clickable on the online version. So let's start by looking at what's happening here. We have two pulses that are going to interfere with one another constructively. So the resulting wave superposition, when these do align perfectly, will be constructive, completely constructive interference. Now let's look at the schematic on the right side here, and we can see if we're adding wave 1 and wave 2 and looking at the resultant wave, here we have maximum positive amplitude. So we're going to add x plus x, amplitude for wave 1, x, plus amplitude for wave 2x, resulting in an amplitude of 2x. Okay, if we look at where we have the maximum negative amplitude under the origin here, we see that we're going to be adding the negative x plus negative x equals negative 2x. All right. And then we have our intermediates between as well. Of interest here might be right in here, where they are both at the origin, and that is where they cancel here. There would be 0 at that point. So looking at this further, let's see what's going to happen as these move toward one another. We start at time 0, each moving 10 meters per second. So after half a second, they would advance to this location. They're both still moving, one moving right, one moving left, half a second. Then 1 second later, you should have sketched that they are constructively interfering with one another at this exact moment. And you notice that this pulse is on top of this pulse at that moment. So you can kind of see, you see that going on right here. I'm going to draw this line a little thicker so you can really see. So that's should be what you have sketched in. And what occurs half a second later? Well, half a second later, we have our pulse that was originally moving to the left is continuing its movement to the left. And the pulse that was propagating to the right continues propagating to the right. So this is the 1, 2, 3 different sketches that I wanted you to get from the wave superposition supplement. Oftentimes for an FRQ, you may be asked to sketch the resulting superposition. So this is great practice for you. All right, question 28. A guitar string of length 1 meter is plucked, creating one standing wave as shown below. What is the wavelength? Well, recall from the preceding facts that the wavelength of a standing wave is twice the node-to-node difference. So if we look at this diagram here, we have a node here, antinode here, and a second node here. Now, just visually, if you were to look at this, you can see that this is half of a cycle. This is half of a wavelength. So it should make sense that lambda is equal to 2 times the node-to-node length, or 1/2 of the wavelength. All right, so let's go ahead and look at a very important animation to help you understand this idea of standing waves as we approach our discussion of harmonics and some of the upcoming questions. So let's go ahead. I'm going to number these 1, 2, and 3. Wave number 1. This is the incident wave that is propagating to the right. It then hits a fixed end at a boundary, and that boundary is where this is fixed. Well, recall what happens to the wave as it reaches a fixed point or boundary. It's going to invert and reflect back in the opposite direction. That's representative of number 2 for this animation. So number 1, the wave propagating to the right, it hits a fixed end. It reflects and inverts and heads back to the left in number 2. And number 3, what you see there is the resulting superposition of those waves interfering with each other, both constructively and destructively, which under the right conditions can give a standing wave pattern where we have a series of nodes and antinodes. It's a very distinctive pattern, whereas any other combination would give some irregular pattern. Okay, so if you again take a moment, look at this animation, you can see on the superimposed wave number 3, we have 2 points here. Call them points P and Q, where P is a point that has no vertical displacement, has no vertical velocity. In fact, it is not moving. That is a node. A node is an area that has no displacement. All right, so it is not moving. Now let's look at point Q. Q is moving vertically. It has a maximum vertical displacement, both positive and negative. If you follow that point and look at when it has a maximum positive amplitude, you will note that that is exactly when the waves 1 and 2, the original incident wave and the reflective wave, add constructively with positive displacements. Now, if you focus on when the point is down here, that is when wave 1 and its reflective wave 2 have interference, again constructively, but both have a maximum negative displacement when they interfere constructively. And again, a node is an area of maximum destructive, complete destructive interference, and at a node, there is no displacement for a point on the medium. All right, now we're ready to do this problem. Okay, so we're going to recall this wavelength, the distance known as a cycle from this point to this point is one wavelength, and we use lambda to denote wavelength in meters. So I want you to look at these two diagrams here of the 1 meter string that has been plucked. And I'll put a second one in there as well because I want to give you this visual representation as we move forward into more complex problems. Well, as you can see, if I put them together, hey, that is a full wavelength. That is a complete cycle of 2 pi. So we see this here, and I'm trying to give you that bit of intuition for some of the facts preceding question 28. So this question you can just answer purely conceptually. Well, if that single standing wave is 1 meter and it's half of a wavelength, then 1 times 2 equals 2 meters. That's going to give you a full wavelength, a full cycle. That is equal to lambda. In question 29, we have one end of a rope that is attached to a variable speed drill, and the other end is attached to a hanging mass. We saw something similar several problems ago, except this time we're actually going to be looking at standing waves and harmonics for this problem. So we're going to be looking at the force of tension here, as well as the standing wave pattern. So the rope is draped over a hook on an opposite wall, so it is fixed. When the drill rotates, it has a frequency of 20 hertz. Standing waves of the same frequency set up along the rope. A, determine the wavelength of the waves producing the standard wave pattern. Find the speed of the wave on the rope. And lastly, let's calculate the linear mass density, or mu, for this rope. All right, so we have our overall wavelength to be 3.0 meters. We're given that in the problem. Visually, in this problem, you can see that from here to here is 1 wavelength. Lambda equals 3 meters, which means we can use our wave equation of velocity is equal to the frequency multiplied by the wavelength. If we're given the frequency, we can calculate the velocity to be 60 meters per second. In the next part of this problem, let's look at the hanging 5 kilogram mass and do a free body diagram here. And we can see that the force of gravity here is equal in magnitude, opposite in direction to the tension force. So this hanging mass is the force of tension because they are equal and opposite. Now, if we've done this in lab, you have a good intuition for this already. If we have not done this in lab, this is leading up to one of my favorite labs where we're going to be manipulating the force of tension by changing the hanging mass on essentially what is a modified Atwood machine on the benchtop. Really cool stuff. So we've looked at that, and we can now say force of tension is equal to 5 kilograms multiplied by the acceleration due to gravity, or 50 newtons. So we're going to use our equation that the velocity is equal to the square root of the force of tension divided by mu. That will allow us to easily calculate what mu is in this problem. Because we know 60 meters per second, we calculated that in part B. So now we're going to divide 50 newtons by mu and take the square root of that. We're trying to find the linear mass density in part C of this problem. Algebraically, we can rearrange this equation and solve for mu to be equal to 0.014 kilograms per meter. Question 30. A guitar designer is designing an instrument in which the speed of the waves on the string should be 450 meters per second. How long must the string be to produce the first fundamental frequency at 370 hertz? So we are looking to produce the first harmonic, n equals 1, the fundamental harmonic. So we have our a schematic here to give you that visual representation of n equals 1, n equals 2, n equals 3 for a string that is fixed at both ends, which is what we're dealing with here with this guitar string. We also have our relationship between the length of the string and the wavelength lambda. And we've gone through this in several of the preceding problems. And you already know that for a string fixed at both ends, that we're going to have the harmonics set up in these discrete intervals of 1/2 lambda. So let's now use an equation to help us to figure out how long the string must be given the variables in this problem. Recall in the preceding facts and in the classroom, I've gone through and manipulated these equations, rearranging one, substituting it in for the other. You can see that at the bottom of the screen here. We have a number of relationships that will allow us to compare harmonic number, speed, velocity, frequency, and the length of the string, or coming up soon, the length of the column. All right, so here we have frequency is equal to the harmonic number, which is 1, multiplied by the velocity, 450, divided by the twice the length. And that 2L comes from this basic property here that we've already discussed in preceding problems. So now you simply need to rearrange this equation algebraically to solve for the length of the string that would satisfy these requirements of having a velocity of 450 meters per second at a frequency of 370 hertz. So we find the length of this string to be 0.61 meters for this problem. Now, there is an alternative solution, as with many of these. You know that's what I love about physics. So whichever one is more intuitive to you is the one I would always encourage you to use. So here in this alternative solution, we can look at our equation for the velocity of a wave is equal to lambda times frequency. Well, we're given the desired velocity to be 450 meters per second and the frequency to be 370 hertz. So using the wave equation, we can then solve for lambda, which is the wavelength, to be 1.22 meters. We also know that for a string attached at both ends, the length of that string is equal to 1/2 of lambda. Those discrete intervals of 1/2 is where we see this standing wave pattern. Therefore, the length is equal to 1/2 of our newly calculated lambda of 1.22, which gives us an answer identical to the first approach of 0.61 meters. Question 31. A string of length 12 meters that is fixed at both ends. supports a standing wave with a total of 5 nodes. What are the harmonic number and wavelength of this standing wave? Again, recall several of our expressions that were derived in preceding facts on the problem set. I've also included a diagram here, a visual representation to help us solve this problem. And as you can see here, we have the fundamental n equals 1. But for this problem, we have 5 nodes. 5 nodes. Well, for the fundamental, we have 2 nodes. For the n equals 2, we have 3. N equals 3, we have 1, 2, 3, 4. And then we get to the 4th harmonic, and you can count a total of 5 nodes. So the harmonic number for question 31 for this particular problem is n equals 4. This is the 4th harmonic in this one. I'm going to cross that out. That shouldn't be there. N equals 4. And then what is the wavelength for this string? We can use a number of our equations that relate the length of the string to the wavelength. So I have here that the length of the string is equal to 1/2 lambda multiplied by the harmonic number. And our harmonic number is 4. So if we plug in numbers here, we can solve for lambda, and lambda is equal to, we know the length to be 12 meters, we know we're multiplying by 2, and we also know that this is the 4th harmonic. Lambda equals 6 meters. So this distance from here to here is equal to 6 meters, and if we go an additional wavelength, we get 12 meters. So again, that shows us our relationship. You can also look at the node-to-node difference. From node to node, we have a distance of 3 meters, 6 meters, 9 meters, 12 meters. However you want to do it, I'm good with that. In question number 32, we have a string of length 10 meters. A mass of 300 grams is fixed at both ends. And the tension in the string is found to be 40 newtons. I think we know where we're going with this one. What is the frequency of the standing wave for which the distance between the node and the closest antinode is 1 meter? All right, so velocity is equal to the square root of the force of tension divided by mu, where mu is the linear mass density, the length is in meters, the mass in kilograms, so base SI units, so kilograms divided by meters will be our units, and our go-to wave equation, velocity relating wavelength and frequency. So as you saw in a couple problems, I've taken this here, which is equal to wavelength multiplied by frequency, and I have substituted this into this equation here because that is equal to the velocity. Then we can look at mu. Well, we're given the mass of the string. Be careful, please make sure you bump that decimal 3 to the left and get it into SI. We need it to be in kilograms, don't make that common mistake. Divided by 10 meters gives us the linear mass density, or mu, equal to 0.03 kilograms per meter. Now we have everything we need. We know the force of tension is 40 newtons. We just calculated mu. We set that equal to velocity expressed in terms of lambda and frequency. Here is a visual representation of what's going on here. I want to look at this real quick. Node, and the distance from the node to the closest antinode is 1 meter. Very important there. Always do some sort of little sketch on these if you're able to. So if that distance is 1 meter, what is lambda? 4 meters. Okay, again, you can see that here. 1 meter, 2 meters, 3 meters, 4 meters. Okay, regardless of the actual pattern and harmonic, if that distance is 1 meter, then it's 1 times 4. We have 4 meters is equal to lambda. So now we can solve for frequency to be 9.1 hertz. 9.1 hertz. So now let's look at our length. The length of the string is equal to 1/2 multiplied by lambda multiplied by the harmonic number. And we're going to go ahead and figure that out just for fun. So the harmonic number n is equal to 2L divided by lambda. And we have the information that we need here. We know the length to be 10 meters, and we know the wavelength to be 4 meters, so we can solve for the harmonic number. So this is harmonic number n equals 5. This is the 5th harmonic, which looks like this. Okay, so here we have the 5th harmonic represented, and we've gone through and had a great discussion about this particular problem. Let's move on to question 33. We have a diagram, and it shows air displacement of 4 standing waves inside a set of organ pipes. Assume the velocity of sound in air is 343 meters per second. On the AP exam, you'll be given that value. It'll be an approximate value, as you know. We're going to just use 343 meters per second here. We're asked to find what is the highest frequency of the wave shown, what is the lowest frequency, what is the longest wavelength, and what is the shortest wavelength for this problem. And in the preceding facts, we started to now talk about harmonics in a column open at one end and columns open at both ends. So this problem is an application of that. For these first diagrams, from the left, 1, 2, 3, we have a column or pipe that is open at one end. For that situation, we are looking at using this equation here. And so we've gone through in class about the idea that this fundamental harmonic n equals 1 is 1/4 of lambda, or a wavelength, if you're wondering where that 4 comes from in the denominator. Now, for the pipe on the far right, it is open at both ends, and that would be, in this case here, we have n equals 2. We've gone over that as well. And for this particular example here, we see that we have we're back to our 1/2 of a wavelength for that particular situation of a column or pipe open at both ends. So it is the same as a stretched string fixed at both ends. So this equation is the same. And I'm going to move on. Let's look at an animation here. So here we have a pipe that is open at one end. Okay? And I want you to take a look at this and think for a little bit about what's occurring here. So that would correspond to these first 3 on the far left of our problem here, where we're using the equation that has 4 in the denominator. Okay, so what we're seeing here is that this is actually n equals 5 is what you're looking at here. And for a column open on one end, there's always an antinode at the open end. There's always going to be a node at the closed end. Okay, so you're going to have a node here. You're going to have an antinode on the open end. And to satisfy that requirement, we get standing waves that can only occur in odd integers, 1, 3, 1/2, or excuse me, 1, 3, 5, 7, and so on for the harmonics. We've gone over this in class, so I'm not going to go through that anymore in this particular problem. Now, let's look at a pipe or column open on both ends, which we are going to be using this equation to look at that. When it's open at both ends, we have that relationship of lambda being twice the node-to-node difference, or distance, excuse me. And so we get these discrete intervals of 1/2, 1/2, 1/2. Okay, so what you're looking at here is the second harmonic, n equals 2, for a column open on both ends. And what's cool about both of these animations is they're actually giving you a cool representation of the movement of the medium, which is air, is from left to right, back and forth, left to right. The propagation is also left and right, because we are dealing with sound waves. These are longitudinal waves. Okay, so let's get to the problem. I'm going to number these 1 through 4 from left to right so I can refer to specific calculations. Let's calculate the frequencies. For number 1, we have a pipe closed at one end, open at the other end. We're going to use this equation because the length for number 1, if you look at the length of the column, it is 1/4 of the wavelength. We have a node at one end. We have an antinode at the open end. This is the fundamental harmonic for a column or pipe open at only one end. So, using this equation and the values given in the problem, including the velocity of the speed of air, the speed of sound in air, 343, and we have our fundamental harmonic n equals 1. We also have 4 in the denominator for reasons I've already gone through repeatedly. And then for the length, we are told for all 4 of these, their length is 0.5 meters. That's where that came from. So now we can calculate the frequency to be 172 hertz. Moving on, number 2, which is also a column or pipe that is open at one end and closed at the other, using the same equation, except this time, please note, this is n equals 3. So the harmonic number n equals 3. So our relationship here is going to be that we have 3/4 of a wavelength. And when you look at diagram 2, visually, I hope you can see that this is 3/4 of a wavelength. So our value here, 514 hertz for number 2. Our last column or pipe that is open at one end and closed at the other end, we're going to put in our values here, but your harmonic number is 5. In the animation I showed at the beginning of this problem, that was the animation I showed for a pipe open at one end, closed at the other. That was n equals 5. Feel free to rewind the video a little bit and look at that again, please. And so we're going to calculate frequency here to be equal to 8.58 hertz. Now, some of you can perform this ranking task without really doing these computations, and that's perfectly fine with me. You know, in these podcasts, I'm going to give lengthy solutions to ensure you understand these problems. So I'm going through all of these calculations, and we find in the first 3 that pipe number 3 has the greatest frequency and therefore will have the smallest wavelength. Pipe number 4 is different. It is open at both ends. This is going to be our equation. It is the same equation that is used for a stretched string fixed at both ends. So these are the same, where we have 1/2 of our lambda. So with numbers in here, and you must be able to identify which harmonic this is. This is n equals 2. N equals 2 for pipe number 4 here. And because the pipe is open at both ends, we must have antinodes at both ends. And then, of course, you see our nodes there are areas of no displacement in the column as well. Let's get a number here, 686 hertz for our final pipe open at both ends. Next, let's look at the velocity and our wave equation. Velocity equals frequency times wavelength, because that's going to allow us to simply convert lambda. Okay, now that we know the frequency and we know the velocity is the speed of sound in the air of 343, we can calculate lambda very easily with this. And if you notice, here's the relationship that we expected. As frequency goes up, wavelength goes down. So which pipe has the smallest wavelength or lambda? That would be pipe 3. Pipe 3 has the smallest wavelength, and pipe 3 has the greatest frequency. So just as we expected, now which one do you think is going to have the greatest wavelength? Well, you can see right here on the screen, that's pipe 1. Pipe 1 has the greatest value for lambda or wavelength, and it also has the smallest frequency, given a velocity of 343 meters per second. All right, question number 34. A musician is designing a custom instrument which utilizes a tube that is open at both ends. Given the speed of sound in air is 343 meters per second, how long should the musician make the tube to create 440 hertz, an A, as the instrument's fundamental frequency? N equals 1 is what you need to be thinking for the fundamental frequency. You are looking at a schematic of the fundamental frequency for a pipe or column open at both ends. All right, and we've talked about this in class. We have a node here. At each open end, we have an antinode. All right, these correspond with areas of different pressure. However, if you look at this and consider extending what the distance would be to help you visualize, as we've done in class, you can kind of get that idea here of the mathematical relationship. So if from here to here is one wavelength or lambda, this distance from here to here is 1/2 of lambda. All right, so frequency is equal to the harmonic number multiplied by velocity, that quantity divided by twice the length of the column of the pipe. Now, using this equation and the intuition that I just gave you, we can plug in our values. We're given the frequency at 440 hertz, which corresponds with an A note. And then we have N equals 1. We have the speed of sound and twice the length, which comes from the relationship between the length of the column and lambda or wavelength. So solving this now, we can rearrange it algebraically, and we can find for the length, we get that this musician should go ahead and utilize a tube that is 0.39 meters long. That's how long the musician should make this tube for the fundamental frequency. Question 35. A car's horn is producing a sound having a constant frequency of 350 hertz. If the car moves towards a stationary observer at a constant speed, the frequency of the car's horn detected by the observer is going to be which of the following? Please recall in the preceding facts for the AP exam this effect, the Doppler effect, it's small. So at normal speeds of, say, 200 hertz, we're looking at frequency changes that are detectable by the observer of tens of hertz, not hundreds of hertz, because you may get an MCQ that has differences of Doppler effect that are over 100 hertz different. No, tens of hertz is the detectable difference. So we have an animation here and a schematic diagram with the ambulance, and we see that as the ambulance rushes past guy number 1 toward guy number 2, the second individual, we have the higher frequency, the higher pitch, whereas individual 1 experiences a lower frequency and lower pitch, which gives that Doppler effect. And we also see that on this animation here as this point moves from left to right. We can see the waves scrunched close together, close, and getting further apart on the left side. So if we have a 350 hertz and it's moving toward the observer, we're going to want to choose an answer that is greater than 350 hertz. And notice again, it's tens of hertz greater, not 100 plus hertz, because the Doppler effect is only detected by differences in tens of hertz. All right, so that is the answer, 380 hertz for question 35. And question 36, we're looking at vertical lines on a diagram that represent compressions in a sound wave of constant frequency propagating to the right from a speaker towards an observer at point A. You're asked to find the wavelength of this sound wave, i.e. this longitudinal wave. The speaker is then moved at a constant speed toward observer A, and you want to compare the wavelength of the sound received by the observer while the speaker is moving and compare that to the wavelength for when the speaker was at rest. So we have our diagram here given to you in problem 36 on the problem set. I've also included an additional schematic that shows these areas of compression and rarefactions occurring that are characteristic of a longitudinal wave or sound wave in which energy propagates longitudinally left and right, and the medium moves left to right, back and forth. The displacement is in the same direction as the propagation or disturbance of energy. So the wave propagates in the same direction as the medium itself propagates, and that is in contrast to a transverse wave that we've discussed extensively in this unit. Let's get to this question here. For part A, the wavelength is 1/2 of a meter. The wavelength is the distance from one compression to another compression. That is the wavelength. Now, we can see here in this schematic, we have areas of high pressure. The corresponding high pressure is right here, this compression. In areas of low pressure, we have a rarefaction occurring. Important to consider that relationship here between the sound longitudinal wave, which is a pressure wave. So the schematic given in this problem, on the problem set, you're measuring, you are told that these lines represent compressions. How far is it from a compression to a compression? From a compression to a compression, that is the wavelength. Well, it is 1.5 meters. From 1 to 2.5 is the distance between those two successive compressions. In part B, it's moved toward observer A. So here's A hanging out right here, and it's moving to the right toward A. Well, we know what's going to happen here. We talked about this in question 35. The observed frequency is going to be higher. It's going to have a higher pitch, Doppler effect. Well, if the speed is equal to the frequency multiplied by the wavelength, and if the frequency goes up, speed stays the same, what are we going to see happen to the wavelength? It's going to go down. In question 37, you are asked to go back to question 7, one of your favorite questions, I'm sure, possibly the longest question in the history. All right, A, B, C, D, E, F, G, kept going. And examine the sketched graphs that you drew, the sinusoidal graphs that you did earlier in this unit. And now we're going to consider a spring block system in which there is a damping. In the preceding fact, you learned that this damping of a spring occurs because of the existence of non-conservative forces. So we have been dealing with ideal springs. Well, in reality, springs have damping, and that damping from non-conservative forces can change and decrease the energy over time, as you see in this vertical spring block oscillator in which damping is present. So you are asked to create a sketch of the potential energy and the kinetic energy. Let's look at what that would look like. The kinetic energy is in blue, the potential energy is in green, and as you can see, when the potential energy is at a maximum, the corresponding kinetic energy is at a minimum. And when the kinetic energy is at a maximum, the corresponding potential energy is at a minimum. Look at the effect of damping here on energy as a function of time. You see it decreases over time. Also in red is that total energy, total mechanical, including both kinetic and potential, and that decreases over time as well. Let's look at the amplitude. Amplitude is going to show here that we have amplitude, whether it's a positive displacement or a vertical displacement above the equilibrium position, amplitude gets less and less over time. Okay, again, this is relating the positive displacement from the equilibrium and the position below or negative displacement in reference to the equilibrium position of the spring is decreasing over time. And that makes sense. We can see that in the animation of the vertical spring block oscillator. Okay? All right, so in question 38, you're asked to rank spring block oscillators in this diagram. You're asked to rank them from highest to lowest in terms of their equivalent spring constant and their period of oscillation. Now, in lab, you were able to explore both a series and parallel combination. In fact, you've derived both of these equations. So let's go ahead and use these equations to calculate the equivalent spring constant for these 4 spring block oscillators. Let's go ahead and start with A and C, which are showing a series combination. So using our equation, we can show that the inverse of the equivalent spring constant is equal to the inverse of the individual spring constants. We can calculate that to be 4 newtons per meter for A, and for C, along that same line of logic, we can calculate its equivalent spring constant to be 7.45 newton meters. Now let's look at diagrams B and D. These are parallel. Parallel are simple. You add the individual constants. So for B, we would get 10 plus 15 or 25 newtons per meter. And for D, you're going to get 20 newtons per meter, which will allow us to go ahead and rank from highest to lowest to answer part A B greater than D greater than C, with A having the smallest spring constant of a mere 4 newtons per meter. Now, for the next part of this, we're going to look at the period of oscillation. In other words, the amount of time to complete a cycle. Let's look at this equation and use mathematical reasoning. Please note that when we look at the period and the spring constant in this equation, that the spring constant K is both in the denominator and under the radical. So in other words, we can say that as K goes up or increases, the period of oscillation goes down or decreases. So our answer to part B is going to be the opposite order of what we had for part A. So we're going to have that our greatest period, or the period that is the longest, is A. A corresponded with our spring constant that was the smallest, again, only 4 newtons per meter. Let's move on. In question 39, a piano tuner is using a tuning fork to adjust the key that plays the A note above middle C. The frequency, 440 hertz. The tuning fork emits a perfect 440 hertz. However, when the tuning fork and the piano key are both struck, beats of a frequency of 3 hertz are heard. Recall that the beat frequency is equal to the frequency 1 minus frequency 2. Well, in this problem, you're actually given the beat frequency. So you need to try to figure out frequency 2, given that you know frequency 1 to be 440 hertz. Also take a look at this diagram and recall that the beat frequency occurs when we have 2 waves that are out of phase. If you take a look at the diagram, you will see that there are periods of constructive and destructive interference. Now, what this does is this increased amplitude, it's louder and then quieter during these periods of constructive and destructive interference. So let's go ahead and use our equation here to look at the beat frequency. So we have 3 hertz, which are the beat frequency given to us in the problem. And we know that it's 440 minus, well, if the beat frequency is 3 hertz, it could be minus 437. That's going to give us absolute value of 3 hertz, which is the beat frequency. However, there's another answer here. So we have 3 hertz being now equal to 440 minus 443 hertz. That's going to also give us an answer of 3 hertz. So we don't know if the answer is 437 or 443. So we have to always take the absolute value when calculating the beat frequency. Now, I want you to hear this. This is a 440 and a 443 hertz. So hopefully you can hear that wobbling sound. And again, these are periods of constructive and destructive interference. Okay, so the next part of this question says the frequency is too high. So should the tuner tighten or loosen the wire inside of the piano in order to tune it? So we're talking about the force of tension. We're talking about the overall frequency and the wavelength and all that. So let's look at some equations and try to figure this out mathematically. So velocity is equal to the square root of the force of tension divided by mu. Mu being the linear mass density of the string, in this case, of the wire. All right, so looking at this, you can see if the force of tension goes up, the velocity also goes up. Now, of course, the tension force is in the numerator under the radical. So we're always mindful of that. However, we can simply say, if we increase the force of tension, we increase the velocity. Well, let's look at this equation here then. Frequency is equal to the harmonic number multiplied by the velocity divided by twice the length of the wire in this case. Well, the length of the wire is the same, and we've already said if we increase force of tension, we increase velocity. Looking at this second equation, we see that the frequency is directly proportional to the velocity. So if velocity goes up, so does the frequency. So the answer is that we should loosen this wire and decrease the force of tension because this would decrease the frequency. I'll see you guys in class.